Hey everyone, so in this supplemental video, we're going to do another example of volumes by revolution. And right from the get-go, I want to give us two spoilers of what this example is actually going to illustrate. The first thing for us is this is going to be another example of us revolving a volume about a vertical line. So we're going to get to change all of that information in terms of y integrals, integrate with respect to y and stuff like that. The other thing that I'd like to point out is in this example, we're going to see that the inner and outer radius changes across some point in the integration domain. Because the inner and outer radius are going to change, we're actually going to split this into two separate volume integration problems. So those are the key aspects to illustrate from the get-go. But the problem we're going to consider is the volume, or we're going to consider the region that's bounded between these subsequent curves. So let me just sketch that out for us for a moment. And those curves for us are the functions y equals x. And then we also have the function y equals 0. So again, just trying to sketch out our curves so far. And then we're also told we have the lines x equals 4 and x equals 6. So this is the volume that we're interested in. So let me sketch this out. So say this is x equals 4, and somewhere around here is x equals 6. So it looks like the subsequent volume that we're interested, or the region that we're interested in revolving, is this region in purple, this region highlighted there. So that's kind of the first step. Let's just try to identify our region of integration. And the next step that we're told in this problem is we're rotating this function or this region about the line x equals 1. So let me stick in that line x equals 1. And that is our axes of revolution. All right, so this is the problem as it's set up so far. Let's get to it and going through our steps for this problem. So with all volume problems, the first step that I like doing is just making sure I identify the axes of revolution. And I know we just said this a moment ago, but right now we have the axes of revolution is x equals 1. And I just want to point out that this is going to be a vertical axis for us. Just so we know, because this is going to be a vertical axis that we're revolving around, we're going to integrate with respect to y rather than x. Step 2 in this problem is defining our radii. And for us in this particular problem, this is going to be interesting because usually we're looking for the outer radius and inner radius from our axes of revolution. So remember, the radii is the distance between the function we're revolving around and the axes that we're revolving it about. So in this case, we are considering, again, this whole region here. But we're revolving this around that vertical line. So if we revolve this entire region about this vertical line, or say we just pick a point along this curve, we know we're revolving this in a more horizontal fashion. And the reason I want to highlight that is we're going to start defining our radii now. So if I start from the axes of revolution and just point towards the function, well, it looks like our outer radius is associated with that vertical line x equals 6. And our inner radius is associated with that vertical line x equals 4. However, if we try doing the same exact exercise up top, we will see that, well, our outer radius is still associated with what looks like x equals 6. But the inner radius is now associated with the line y equals x. So in this example, we see the definition of the inner and outer radius actually changes in this case. Previously, our inner radius looked like the distance between our line x equals 4 and the axes of revolution. However, once we get vertical enough or just increase enough in y, we see that changes because our inner radius is now going to be associated with that function y equals x. So what this really means for us is we can think about this as splitting across two different integration regions, or for two different regions. So we could think about this top piece as region 2 and this bottom piece as region 1. And the reason we think about this is region 1 and region 2 will have their own outer radius and inner radius as well. So let's think about this for a moment. So let's think about the region 1. What is our outer radius? Well, the outer radius in region 1 looks to be the distance between x equals 6 and our axes of revolution. So the outer radius would be 6 minus 1. And the inner radius in this region looks to be the difference between x equals 4 and our axes of revolution, x equals 1. So let's think about this for the second region now. In region 2, our outer radius, well, that still looks like the distance between x equals 6 and our axes of revolution. So we still have 6 minus 1. But the inner radius now is associated between our function y equals x and that axes of revolution. So remember, our function y equals x, we need to rewrite this function as, well, x is a function of y, which I guess in this case is just x is equal to y. So our inner radius in this case would be the distance between that function, x equals y, and our vertical axes, x equals 1. So in this case, it would be y minus 1. All right, so we have our inner and outer radii defined. And again, we have two separate volume integrals now because we have that piece on the bottom that we're revolving and we have that piece on top as well. So because of this, finding the bounds, we're going to get to think about a bit because we have two separate integrals, two separate volume integrals in total. So our integrals in this case will have different bounds depending on whether we're in region 1 or region 2. So let's just point that out. Region 1 will have its own bounds. And region 2 has its own bounds as well. So we'll do the same exact process. We'll first start thinking about region 1 and then think about region 2 afterwards. So let's go back to our plot. And again, this is why our plots are so tremendously helpful here. So let me actually just color in our region here, just so we can highlight different aspects. All right, so region 1, I'll highlight as this bottom piece. And remember, we're integrating with respect to y here because we're revolving around a vertical axis. So we need to ask ourselves, what is the smallest y value for this region? And what's the highest y value in this region? So for us in this region, I would say this is the lowest y value. And right here is the highest y value. Literally just because when we look at the y-axis, this is what happens. So we need to think about how to get these values. Well, for us, that lowest y value just happens to be at y equals 0. So we can say the lower bound in region 1 is y equals 0, but we need to figure out the higher bound or the upper bound. And when we think about the upper bound, well, what we noticed from our idea that region 1 ends there, the upper bound is associated with whatever that y value is. How can we find that y value? Well, for us, it turns out that y value will be the intersection points of our functions there. So let's think about those functions for a moment. The function there was the function x equals 4, and it intersects with the other function, x equals y. So we need to find the intersection point there by basically setting those two functions equal to each other. So if we set those functions equal to each other, we have our function x equals 4 and our function x equals y. So we set those equal. And basically what we just find is, well, y equals 4. If we just set those right-hand sides equal, we find y equals 4 is the upper bound. So that would be the upper bound for region 1. All right, now that we have the lower bound and upper bound for region 1, let's move on along to, that's right, region 2. So going back to our plot, let's think about who region 2 is here. So let's try to get rid of some of this extra information and highlight what region 2 is. So region 2 for us was kind of this upper triangular piece. And we need to think about now who the upper and lower bounds are for region 2. So remember, we're integrating with respect to y. So we're sort of looking at which is the lowest y value and which is the highest y value in that particular region. So I would say down here, this is the lower bound for region 2, while the upper bound would be associated with this point up here. Or maybe not point, but the y value of that point up there. So we need to figure out what these points are. Well, for us, luckily, we already found out what that value of that lower bound was. Remember, we saw that the value of that lower bound was the intersection point between the functions x equals 4 and the function y equals x. So we already found that lower bound, and that lower bound in this case is y equals 4. And again, just to clarify, that was our intersection of two functions. And that was what we did in the previous example, or in the previous region 1. So again, we're stuck with figuring out what is that upper bound. So let's go back to our plot. So the upper bound was associated with that y value that basically gave us that value up there, the highest y value inside of that region. And how can we find that? Well, we need to find the intersection point of two things. We basically see at that particular region that there's an intersection of the function y equals x, and there's an intersection of the function x equals 6. So we're going to get to set those two functions equal to each other to find that upper bound. Again, that was our function x equals 6 and our function x equals y. So for the upper bound in region 2, we have our two equations that we'll set equal to each other. We had x equals 6 and we had x equals y. Again, we're thinking about these bounds in terms of y because we're revolving around a vertical axis. So we'll set these equal to each other just like we did in the previous problem to find that upper bound in region 1, or the lower bound in region 2 for that matter. So setting these right-hand sides equal to each other, we can set y and 6 equal. So we just find that y equals 6, and that would be our upper bound. Again, sometimes when we set these functions equal to each other to find intersection points, we might get to do a little bit of algebra like we did in class, but in this example, we see that that upper bound just pops out at us. All right, so that brings us to step 4. In step 4, put it all together. And I want to do this piece by piece. So let's first think about region 1's volume integral. So we can write our stencil for our volume integrals that we'll fill in a moment. So in region 1, we're integrating with respect to y because we are revolving around a vertical axis. The other thing we found for region 1 was that the lower bound was y equals 0, and we saw the upper bound was y equals 4. And then the last thing we needed to do was figure out our inner and outer radii for that specific region 1. So in region 1, our outer radius was 6 minus 1. Our inner radius was 4 minus 1. So let's type those in. So 6 minus 1 for the outer radius and 4 minus 1 for the inner radius. Oh, I need a square there. So just to clarify, 6 minus 1, that was our outer radius, and 4 minus 1, that was our inner radius. And that was the region then for volume 1, or volumes 1 region in region 1. And I will just give that a little volume 1 flag. That is the volume of region 1 there. So let's do the same exact thing for volume 2 from region 2. So the volume in region 2, that was that upper triangular piece. We'll have the same kind of integration stencil. And then we can fill in these pieces accordingly. So again, in region 2, we're still integrating with respect to y because we're revolving around a vertical axis. So these integrals are dy integrals. The next thing we saw were the upper and lower bounds for region 2. And that was y equals 4 and y equals 6. And remember, these upper and lower bounds, if we go all the way back to our drawing, we're associated with, if this is region 2, I'm just highlighting now, they're associated with the lower bound of that region. And since we're integrating with respect to y, the lowest y value of that region. And then we go all the way to the highest y value of that region at that very top point of that triangle. And we saw that these bounds for region 2 were y equals 4 and y equals 6. All right, the last thing for us to do then is plugging in those inner and outer radii. And for us, we saw that the outer radius, the distance between the function furthest from the axis of revolution and the axis of revolution itself, was 6 minus 1, whereas the inner radius was y minus 1. So remember, if we go back and think about those radii, the distance between the axes of revolution and the functions that we're revolving around, the outer radius is associated with the function that's furthest from the axis of revolution. So in this case, it's associated with that x equals 6, whereas the inner radius is associated with that closer function, which in this case was our function y equals x or x equals y. So let's plug those values in. We had for region 2, the outer radius was 6 minus 1, and the inner radius was y minus 1. And that's basically it. So we found the volume of each of those regions separately. The last thing we would do is say the total volume. Well, the total volume is going to be the sum of both of those regions' volumes together. So the next step we would really do here is just add all of those integrals together. And that's how we can set up these volume integrals when we have different definitions of the outer and inner radii, depending on where we are within that integration overall domain.